The automotive sector has spent billions and logged millions of miles, but hit a wall. Most commercial systems remain stalled at Level 2 and Level 3 autonomy. These are systems that can steer and brake under optimal conditions, but strictly require a human to intervene when the computer fails. That stagnation is a direct result of how machine learning models are trained. The vast majority of the data collected by fleets today consists of sunny day scenarios, predictable, low-variance environments that teach the vehicle how to behave when everything goes exactly right. This chart shows the reality of that data collection. The massive bulk on the left represents nominal highway driving. It provides a high volume of information, but that information is entirely repetitive. It yields very little new educational value for the underlying artificial intelligence. Moving down the curve reveals the long-tail barrier. These are the rare, unexpected, and highly impactful situations, like severe weather, erratic pedestrians, or mechanical failures. When current autonomous models encounter these edge cases, they fail. Deploying more test vehicles to drive in straight lines on public roads cannot solve this. Edge cases are statistically so rare that waiting for them to happen organically will never yield the volume of data required to properly train a machine learning algorithm. To bypass the slow pace of physical driving, the industry relies heavily on synthetic software simulators, operating under the assumption that missing edge case data can simply be coded and generated virtually. But synthetic environments model idealized physics. They calculate traction, mass, and momentum based on perfect algorithms. They do not accurately replicate the uncertified chaos of a degrading road surface, unpredictable tire wear, or complex aerodynamic drag in a storm. That discrepancy between how an autonomous system reacts in a flawless simulation versus how it behaves in physical conditions is known as the sim-to-real gap. This image shows a direct comparison between a simulator physics environment and real-world track telemetry. To make the top left simulation accurate, engineers must correct its base physics engine. That requires injecting actual high-G adversarial data recorded in the real world back into the simulation software. If developers attempt to bypass physical ground truth calibration, their simulated AI models will overfit. They will master the perfect virtual world, but instantly fail in zero-shot real-world scenarios, situations the vehicle has never explicitly encountered in its training data. To capture that required physical chaos, closed track racing and extreme motorsports are utilized not as competitive entertainment, but as tightly controlled R&D laboratories. This diagram illustrates the difference in data density. A typical highway commute is 99% noise and repetition. In contrast, an extreme track environment is 100% signal. The operator constantly pushes the limits of friction and physics, generating high-value edge case data every single minute. Extracting this data requires component-level validation. Custom vehicles are stripped down and instrumented with experimental hardware, including LiDAR, sensors that use poetry forced into failure under extreme heat, vibration, and gravitational loads. When a component breaks under these conditions, it provides a universal boundary limit that hardware manufacturers can use to evaluate their designs. Intentionally inducing these mechanical failures and precisely digitizing the results provides the exact ground truth calibration that synthetic simulators lack. If extreme physical data is the only way to achieve true Level 5 autonomy, where a vehicle drives itself entirely without human input, the obvious question is why global automotive manufacturers aren't capturing it themselves. The barrier is risk. Major manufacturers are bound by rigid legal and regulatory constraints. They cannot deliberately induce high-speed crashes, push vehicles to catastrophic traction loss, or test uncertified hardware publicly. This flowchart outlines the solution: the liability firewall. An OEM, or original equipment manufacturer, remains completely shielded from operational hazards. Instead, a specialized third-party proxy operates on the other side of the firewall, running the dangerous physical data extraction. Because the proxy fully assumes the operational and legal exposure of extreme motorsports, risk-averse deep tech clients can simply purchase the resulting data. It arrives on their servers as a clean, compliant asset. Overcoming the long-tail barrier requires decoupling physical risk from the R&D pipeline entirely. The bottleneck is a legal and operational puzzle just as much as a software challenge. Standard industry practice treats human test drivers as unpredictable variables. The goal has historically been to suppress human reaction or remove it from the data loop completely. A more effective approach treats expert operators as knowledge amplifiers. Their immediate physiological reactions to a sliding tire or a sudden obstacle actively annotate complex physical events in real time. To capture this, engineers use cognitive biometrics. This involves outfitting operators with infrared microfacial tracking and EEG sensors, which record the electrical activity of the human brain under extreme physical stress. These biometrics capture a driver's anticipation microseconds before the vehicle's mechanical sensors register a physical anomaly. The human brain detects the initial loss of traction and begins calculating a countersteering response before the digital accelerometer confirms the slide. Digitizing this pre-physics response teaches AI models proactive social logic and adversarial anticipation. It forces the system to upgrade from a machine that merely reacts to a collision to an intelligence that anticipates and avoids it. Recording physical and biological chaos at the track is only the first step. That massive volume of high-fidelity data must be ingested. The raw hardware stack bridges mobile compute labs directly at the racetrack to a private on-premise data center. This is specifically configured to handle intense data loads without cloud latency. Inside these servers, raw mechanical physics, operator telemetry, and acoustic fusion data are synchronized down to the microsecond. This flowchart breaks down the final outputs. The raw data is formatted into ML-ready datasets, perfectly structured for machine learning ingestion, licensed through a data-as-a-service model. The second output delivers pre-trained, containerized AI models for private deployment, structured as AI as a service. Extracting extreme physical data only generates commercial value when that chaos is distilled into privacy-compliant, standardized formats. Enterprise software teams can then instantly plug this into their existing pipelines. This image outlines the primary target market hungry for these datasets: the Tier 1 mega suppliers and the OEMs building the next generation of software-defined vehicles, where core driving functions are governed entirely by updatable code. The physics logic extracted from extreme traction loss and human anticipation is hardware agnostic. It applies to any machine calculating friction, weight transfer, and spatial awareness. This cross-domain knowledge drives the convergence of autonomous systems across land, sea, air, and space. A drone tracking an intersection requires the same predictive social logic to anticipate human movement as a vehicle on the ground. This points toward embodied intelligence, AI systems that physically interact with their environment in real time. These systems inherently understand and navigate physical chaos, regardless of the hardware they inhabit. Achieving full Level 5 autonomy and crossing the uncanny valley of machine operations cannot be done with safe, predictable data. It requires forcing artificial intelligence to confront and learn from the most extreme physical realities humanity can generate.